Hello everyone, welcome back to the course Control Engineering KM31703. Today we will talk about the fundamentals of modeling and control. This topic will be short and it should give you some basic of modeling and the necessary mathematics to form your transfer functions in order for you to model and control in the later stage of this course. First, modeling. Modeling in this sense refer to a set of mathematical equations that are intended to capture the effect of a system's variables responding to a certain other variables acting towards the system. This modeling is important for us to be able to simulate how the system will respond, and therefore we can systematically design a controller for that particular system. Therefore, this modeling would be more on a mathematical modeling of a system that you have learned before in the differential equations. This mathematical model can be classified according to the properties of the equations. For examples, there would be maybe one input and one output, meaning to say one-to-one linkages, okay, where the model equations have only one input variables and one output response. Also, the models can be a linear type of model, mathematical model, or it is a time dependence or time varying model. It also can be categorized as continuous as opposed to the sample or discrete model, input output type, and also a lump parameter type. In many situations of non-linear model, we would try to simplify or linearize the model around the user-defined operating point. This is because non-linear models are more difficult to solve and control. At the same time, as an engineer, we would prefer a system that are simple yet give us the kind of accuracy that are acceptable. So there is always a trade-off between simplicity and accuracy. It is possible to improve the accuracy of a system by increasing the complexity, by increasing the non-linearity of the model that can go up to maybe power of 3 in the order of power of 3 or higher, but that may not be necessary, okay? Therefore, it is a compromise that you should, as an engineer, to determine and analyze accordingly. Linear approximations of physical systems should satisfy two properties. First, superposition, and second, homogeneity. Superpositions refer to the response that produced by simultaneous applications of two different forcing functions, and they can be summed up together as two individual responses. For example, you would have y1 equals to x and y2 equals to x as well. When we combine this or superimpose or superpositions these two response, you would get an additional y equals to the summations of these two response itself. However, as you can see, an equations with order higher than 1 would not satisfy this superpositions property. The second property would be homogeneity. In the homogeneity itself, the magnitude scale factor must be preserved. What it means is that the response of a linear system to a constant multiple of b, let's say b, okay, multiple of b, okay, of an input x, must be equals to the input of, let's say this is x1, okay, it should be equals to another multiple of x2. Therefore, the magnitude scale are now preserved as a constant b. Now look at this linear equations where you have y equals to mx plus c. You would see that this constant itself do not satisfy the homogeneity of the property where it should multiply by a factor of m. But in this case, when the changes of x and y are small enough, then we would consider these systems to be linear. Here we would see the descriptions of a dynamic behavior being translated from a physical system to a block diagram. The first picture shown here refer to a physical system or mechanical system of spring mass damper system. This system can be separated or simplified into free body diagrams as shown here. From this free body diagram, we would be able to model mathematical functions as shown as such using differential equations. Based on this dynamic behavior, we can later on summarize and form into a transfer functions being represented by only blocks. We would later call that as block diagram. So in this course, our main target is to be able to model from a physical system to a block diagram, so that in the later stage we can use several control engineering principle or approach to analyze them and to check what is the response and the stability of the system. This slide shows how we could linearize a dynamic system which have a order higher than 1. In general, the relationships between two variables in a dynamic systems can be given as such: y equals to a functions g, where the g functions indicates yt is a functions of x. So you will see that the yt written here, as you have learned before, referring to a functions of time. So in this system, we would want to know what is the normal operating conditions or point, and here we can designate that as x0. Taylor series expansions about the operating point is now being utilized to our previous functions or relationship between the two variables, such that it is given by a series of terms. The slope is a good approximation over a short range of x minus x naught. Therefore, if we only consider the first two terms, as we always practice, we now would get y equals to y naught plus m x minus x naught. This is something similar to the linear line, right, of a constant plus m capital X. Here is an examples. If we want to know what is the torque acting on the mass of a pendulum in this oscillator itself, we would able to relate them as mgl sine theta. Okay? So you just have to resolve the torque. Torque is equals to length multiplied by the force in these directions, right? Okay, so this force is a component of this weight, okay, mg itself. So we just have to resolve that. You will get the torque, okay, L multiplied by this component of force, okay, to get these functions. Referring to the previous Taylor expansions, therefore the first derivative evaluate at the equilibrium, which is the normal operating point, would now translate or provide a linear approximation as given as such, right? So we would have the terms mgl partial derivative of sine theta over theta multiplied by theta minus theta naught as given as the previous equations, the first derivative, right? So from there, when we further simplify that, our T naught equals to the 0, which is the normal locations, 0, okay, where it is the common point or the normal point where the mass will always go through. Therefore, we will have this T equals to mgl theta, where again, when the angle is small enough, this cos theta will give you an approximation of a theta. Therefore, we have now linearized our equations. Okay, how we would see this in our oscillations. Okay, so this torque will actually oscillate. Okay, however, because of our operating conditions, again, as this pendulum always oscillate in between this angle, so in between a certain range, let's say is less than pi over 2 on both sides, therefore we can approximate this line, and this line actually being approximated by these equations. So you will see that even though this line will continue to oscillate, but our main interest is only this particular sections. Therefore, this straight line would approximate best, okay, when the angle is getting narrower, right? So if our operating regions or range only at this angle, then this linear equations would approximate at higher accuracy, okay? But the further it goes away, then the error of approximation is getting higher, right? So that is the trade-off that you have to understand, okay, when we try to linearize our system or our model. There are several mathematical backgrounds that you should again refresh on your own. But here I would just quickly highlight some of the mathematical fundamentals that you would need to know, okay, and it will be being used throughout this course. The first would be the complex variable. In the control engineering, you would see a lot of complex variable with, let's say, j, okay. So here we would prefer to use j, okay, instead of I, right? So you have s equals to the real component plus the omega j, okay, where this j represent the imaginary component, right? This j, when we multiply by another j again, that will give us -1, right? So this is the property of the complex variables. The complex variables or functions can be also represented by a diagram, okay. So this is a diagram, okay, where we can break this sigma plus j omega into a diagram, okay, given or being represented by a sine and cos component. So you would have this being represented by r cos theta plus the imaginary part as r sine theta, right? So both of them will have a common radius, and when we further simplify this would be equals to r multiplied by exponent of j theta, right? So this is a conversion from the normal complex format, okay, to another format. Right? So how we would represent this r cos theta? So you will see that this is the real component, the x represent the real component and y represent the imaginary component, right? So this would be our r, where we would able to oscillate between this real and imaginary component. Therefore, as a circle, the functions of a circle can be represented by cos and sine, okay. Therefore we have these relationships. In order to get the modulus or the magnitude of the complex number or complex variable itself, we will represent that as a modulus, okay, and that modulus will have the value of r, okay. So this is our modulus r, right? If we are given a complex number, therefore this r can be calculated as the square root of the value of the real parts square plus the square of the imaginary part or the imaginary component value. In order for us to get the angle, okay, we will say that as an argument for s, okay, that would represent by the angle theta, okay, and that would be determined by the tangent of the real divided by the imaginary, this angle, right? So if from the diagram you would able to see this relationship clearly, right? So this is the real part and the imaginary part value. So now once we familiar with these complex variables or complex number, now we will see a complex functions where you would get more familiar in the later chapter, where we will use a lot of this s to represent a complex variable or complex number, right? So we will have a complex functions as a functions of a complex variable, okay. So here we will use s instead of x, right? We will have a lot of fractions in this course, okay, to represent the transfer functions. Besides, this course also require to get familiar with Laplace transform. Laplace transform is, or in Malay we call it penjelmaan Laplace, okay, are used to analyze linear time invariant systems. In this Laplace transform, it would transform a real variable in the form of t, okay, into a complex variable of s. Okay, through this Laplace transform, most of the differential equations can be solved easier. Many non-linear systems have the regions of operating, okay, which we can again being reminded that can be linearized reasonably, right? Or the Laplace transform is actually given by these operators. Okay, we would write L Laplace transform operator on our functions, okay, or variables, which is a functions of time t. Okay, once we transform it, then it will now being converted or transformed into a functions of s, a complex variables. This transformation actually occurs by taking an integral of the function itself multiplied by an exponential minus st, okay, respect to the time, okay, from 0 to infinity. Now we will take these examples or to do a Laplace transform on a step unit. Step unit again is quite a common input response that you will use in control. That's why we will start with the step unit, right? So assume that we have a functions of gt as a step. From time less than 0, it is 0, and once the time is 1 or more than 0, it will start to give you a value of 1, right? So this, if you represent it by graph, okay, so this is time 0, okay, so once it get to more than 1, then it will straight away become 1, okay, just like a digital step, right? So we call this a step unit. Okay, so if we take a Laplace transform of this so-called step unit, okay, which actually eventually you have the u over time, where time more than 0 we will have equals to 1, right? So we take this transformations, okay, for this step unit. So we have the Laplace transform of the ut itself equals to now being transformed to a new functions us, okay, given by the integral of u multiplied by exponential of minus st dt, right? So this ut is 1, okay, so we can see it's 1 as a unit. So as a unit, therefore when we integrate the exponent of minus st dt, we will have 1 over t as our Laplace transform results. Okay? So therefore, the first thing that you need to know is that when we try to transform a step unit or a constant value 1, you will get 1 over s. Then with another important response that we would want to describe using Laplace or transform into Laplace is the exponential response, right? So let's say this is our response gt exponential, right? So just replace this into our Laplace transforms, okay? So we would able to add them up, and eventually you get the Laplace transform of this exponential equals to 1 over s plus a, right? So that would tells you how all these transformations actually occurs, right? But then in this course we will not need you to derive most of the time from that basic. Okay, what you need to know later on is just to apply, right? So whenever we see unit, step unit, right, so immediately you can transform it to 1 over s. Okay, you just refer to the table, right? When we comes across an exponential, then you would know it should be equals to this, okay, when we transform it, right? Same thing for others, where you will have an impulse. Impulse means it just jump for very short. Okay, so impulse, you will get 1. Okay, when we multiply by a constant, we call it ramp input or ramp response, so you will just have 1 over s square. Okay, parabola and so on, right? So this is the table that you would refer from time to time onwards. Okay, keep in mind this is important. Here is also others Laplace transform theorem that you may apply later on, okay, on how to do an operations between them, so that you can add them or multiply or scale them, okay, accordingly, right? So this is for you to refer later on. Once you get familiar with this transformation from a functions of t to a functions of s, then you should be able to do it in the inverse directions. Okay, so remember what our main intention is, to do this Laplace transform to help us to solve our problem easier, our differential equations problem easier, right? So once we have transformed it, we want to inverse the directions, okay, to get back the final solutions, okay, for our main problem. Therefore, you would be able to do an inverse Laplace transform as well. Okay, so this inverse Laplace transform, first thing we have to identify the component within the Laplace transform. Okay, so let's say these examples, right? So we have this already transformed f1 in the as a function of s, given by 1 over s plus 3 to the power of 2. Therefore, what are the components that we have? So if we refer back to our previous formulations, is there anything similar? We would see that the parts that's related to 1 over s plus 2 is related to e minus at ut, right? So we write it down, is related to e minus 3t, right, ut. Okay, so that is the component related to 1 over s plus 3. Then next we will see this square part. Okay, so this square part, again we will check back the same table again, and we will realize that it is related to the ramp. Okay, and this ramp is actually a multiply of t, right? So eventually it means that you have to multiply by a t. Okay, so you will get this answer, right? So this is how you can inverse back your transformation into a functions of t. As I mentioned earlier, fractions will become important part of this course, right? So you'll see a lot of fractions here and there. Okay, and what's additional mathematical knowledge that you need to deal with is the partial fractions expansions. Okay, now we would see how we could use that to find the inverse Laplace transform of a complicated functions. First thing, we would try to simplify the function itself. We would convert that to a sum of simpler term. How we can do that? Let's take these examples or problem. f1s equals to s power of 3 plus 2 s power of 2 plus 6 s plus 7 divided by s squared plus s plus 5. We will notice that the order of the parameters or functions at the top is greater than the one at the bottom. Therefore, we will now able to identify that we can break them into several simpler terms. We would now try to see a quick solutions. Okay. Plus 7. Okay. So in order to achieve power of 3, we need to multiply by s, right? So when we multiply by s, this whole thing will become s power 3 plus s power 2 plus 5. Okay, so disappear, remain s squared plus remain s plus 7, right? So now again s squared, so we can again plus 1. Okay, so we try s squared plus s plus 5. Okay, we still have remaining. Okay, so the remaining is cancel, remain 2, right? So eventually we will be able to write such that it is the summations of s plus 1 plus 2 divided by s squared plus s plus 5. Based on this, now if we want to do an inverse, it would be much easier now, so that we know s is an impulse, okay, given by an impulse. From these three terms, now we can know that or break them into a simpler form, right? So we can check back this s. When we do inverse, it refers to a differentiation. You can see that s is here, right? So it's a differentiation terms, alright? So therefore, we would differentiate respect to the time. Okay? And then 1 refers to the impulse. 1 is the impulse, and the remaining is our Laplace, inverse Laplace of 2 divided by the s squared plus s plus 5. When we deal with the partial fractions expansions, remember there would be 3 type of cases to consider. The first case would be the roots of the denominator, the bottom sections, are real and distinct. Okay? Real and distinct means they are different. Okay, you can see that s plus p1, p2, p3, and so on. Okay, they are real and distinct. The second case would be the real of the denominator are real and repeated. Some of them are repeated, so you would see that they are a multiply of others. So you have s plus p1 to the power of r, maybe power 2, and so on. Okay, multiplied by s plus p1, p2, and so on. Okay, so they are repeated. Okay, so once when we break it out, then we have to now repeat this particular segment, okay, in our for every single terms of these partial fractions. Okay, so this part, okay, so we will take the second part, okay, until the last terms. Okay, so you have to repeat it until the last term for the denominator. Okay, so this is important. For the case 1, easy, whatever you see, you just repeat at the bottom. Okay, so, and for the case number 3, it may involve a complex and imaginary. Okay, so when it involves a complex and imaginary part, you just have to repeat them. Okay, but then when we repeat it, make sure the upper part, the numerator part, will have the complex numbers of form. Alright, so it will be k2s plus k3. Okay, since the highest order of the denominator is 2, therefore the numerator highest order should be 1. Okay, must be less than that. Okay, if this is 3, then this should be 2 plus k2 k3s plus k4 and so on, right? Or we can easily break them into different terms of partial fractions. So here you will see that 2 divided by s plus 1 plus multiplied by s plus 2. So these partial fractions, we can break them into 2 parts, right? So first part, second part, right, with 2 unknown. Okay, based on this, now we will try to solve these equations. Okay, the top part and the bottom part, right? Now when we want to solve this part, okay, what we need to do is we will take these 2 parts and see which this group we want to cancel out. Let's say we want to cancel out the s plus 1, right? So in order to cancel out this s plus 1, we will multiply s plus 1, right? Here we multiply also s plus 1 and also the s plus 1 over here, right? So s plus 1 we can cancel out, okay, cancel out, but not this segment. So when we cancel out, we will see that this is equals to 2 divided by s plus 2 k1 and k2 multiplied by s plus 1 divided by s plus 2, right? Therefore, once we have this relationship, what we need to do is just we substitute or solve them simultaneously. Okay, so you can move here and there in order to get the k1 and k2. We can also do what we did previously, okay, to bring this away, right? So it will become, we multiply by s plus 2. Now we target s plus 2, so this one multiply by s plus 2, and here we multiply by s plus 2, right? So eventually this one cancel out, this one cancel out, right? So 2 equals to k1 s plus 2 plus s plus 1 s plus 2 and k2. Okay, so in this form, then you would be able to solve it easy, and you would get the k1 equals to 2 and k2 equals to minus 2. Once we know k1 equals to 2 and k2 equals to minus 2, then we would now rewrite such that fs equals to 2 divided by s plus 1 plus minus 2 s plus 2, right? So this is one term, this is another term, and we just have to refer back to the previous table and we would get our inverse functions, right? So you can try for case number 2 and case number 3. You should be able to get this answer, right? So make sure you get this answer, then later on it will be useful for you. Okay, Next important fundamentals in the control engineering would be the transfer functions. Transfer functions are commonly used in the control engineering to characterize or to map the input and the output of a systems. It can be described as a linear or nonlinear, and mainly to describe the differential relationship, okay, between them. Okay, so here we would always prefer to use a ratio of the Laplace transform of the output, okay, of the response to the Laplace transform of the input, okay, to represent or to define these transfer functions, meaning to say this would be our ratio. Okay, so this ratio multiplied by the output, the transfer functions can be seen as given in this block or this diagram itself. Okay, so therefore, as being defined, the ratio itself, meaning to say output, this is the output, the CS, okay, divided by the input, the RS, okay, should give you this. Okay, so this is what we call the transfer functions. And in these transfer functions, the assumptions for all the initial conditions are 0. Okay, so once we know this ratio, output divided by input, we would represent them as a block diagram. So block diagram, we will just put the arrow input of RS through this ratio, give us this output, the CS. Mathematically also, based on this, let's say this is our transfer function given by GS, okay, which this GS is this complex partial fractions. So the output now, the CS is equals to the multiply of GS multiplied by the RS, right? So the basic ideas of the transfer functions. Since mathematically it could be complex or maybe sometimes simple, sometimes complex, but then when we combine them together with multiple behavior or characteristics of input and output of different component, here is only represent maybe one component. Okay, let's say this is representing one component. When we multiply or connect them into more than one component, then this diagram would help us to visualize how they are related and where they are related, at which junction they are related, right? So this is the idea of putting our equations into the block diagram first. Okay, here is the test waveform that are commonly used in the control system. What it means by test waveform is that when we try to test a system, okay, we would inject a signal. We call that as a test waveform, right? So the signal can be in the form of impulse, okay, just one signal, right, then disappear, or in the form of step, okay. That's why I've mentioned step response is important, okay, how it is being how it would respond to a step input, a ramp input, a parabola input, and a sinusoidal input. Right, so this kind of input is I would say is mathematical, in the mathematical form. Okay, in ideal or physical form itself, this impulse could be, let's say, your car. Okay, this is a car, okay, going through a pothole. So this pothole itself is just suddenly go down and go up again, okay, as the car go through this pothole. So this kind of movement is something similar to the impulse. Okay, through a certain time there is an impulse signal, right? Whereas for the step, it's just like the car suddenly go down and continue, right? So it can be go down and continue. So it's a step, or maybe go up and continue, right? So your car going up and continue, okay? Bumping up and continue. Ramp, the car may going up a hill, right? Or the ball going down a hill, and so on. So these are the basic test waveform or signal waveform that we try to use, okay, to test how it would respond to this different type of input, okay, when our design systems are implemented in the real environment. Okay, before I forgot, here each of these input impulse are being represented by these functions, right? So just remember, these functions are the representative or mathematical representative of this different type of input, okay? So if the transfer functions of the system is now known, okay, if you know it, then you will be able to study the output, okay, from different input, okay? Just like if you put this input, what would be the output, okay, if we already know the transfer functions, okay? If the transfer functions is unknown, okay, if it is unknown, then it may be needed to be established or being studied through experiments, okay, by introducing all these non-input, okay, and study what is the output. Meaning to say, we would test it using, remember the previous test waveform, okay, we would test it based on this waveform how it would behave, based on another waveform how it would behave, and from that we would deduce what would be the transfer functions of the system, okay? It's a black box and we test with different signal how it will respond, okay? So either it's known and unknown, then we have to approach it differently for the transfer functions. As a practice or revisions, go through this differential equations problem, okay, given by this second order differential equations, how you can solve it step by step through the Laplace transform, okay, in order to get the solutions, right? So just go through it and try it on your own, right? So at the end you would be able to see something like this, okay? Just go through it so that it keeps in your mind, okay, or stick in your mind. This slide illustrates how you can find the transfer functions being represented by a mathematical model or differential equations, okay? For example, this case, okay, dc over dt plus 2c equals to r, okay? So in these differential equations, if you are familiar or recall the general functions of differential equation, you may have dy over dx, okay, plus y equals to x, okay, or others, all right, or c, okay. So first thing you need is to identify what is the input and the output, right? So if the c itself is the input to the system and the r function is the output or the response of the system itself, okay, so therefore when we try to solve for it in order to find the transfer functions, we just have to transform each of these term, okay, into the Laplace form, okay, and then group them together. So here you will see that sc plus 2c, okay, so you can group them as cs bracket s plus 2, let's say, equals to rs. Okay, so now based on this, what would be our input and output? That is the questions, right? Let's say our output here is C again, right? So C, then it would be C over Rs, okay? And that would be equals to this shift over 1 over S plus 2, right? So this 1 over S plus 2 would be our transfer functions. Once we have identified the transfer functions, as we know, if the transfer function is known, now we would be able to identify what would be the response or the output if we are given a certain input and so on. Okay, so let's say here we want to find what is the output or the response to an input. Okay, and this input ut is a unit step. Once we have identified this, okay, what is the input responded you want to test? All right, so if let's say it is a unit step which is 1 over s, therefore we just have to put in to our previous equations given by this, okay, assuming the initial condition are zeros. So the output would be 1 over s multiplied by s plus 2. Okay, so after we get this one, we just have to expand it back to the solutions, okay, or the time domain, okay, into the time domain, right? So now previously is in the s domain, the imaginary the complex numbers domain. Okay, so turn it back into the time domain through the inverse Laplace, therefore we get these solutions. Okay, this would be the response of the systems being given a unit step as the input. Here is another examples of Laplace transform for a differential equation. Okay, so this is mathematical, so you can just follow this problem and the solutions. All right, so try it on your own as the tutorial, and these are the steps how you can do it until the solutions, right? So this is mathematical, and here is an examples of how you would see a physical systems being transformed into the transfer functions, right? It will be assumed that the hydraulic fluid is available from a constant pressure, and that the compressible of the fluid is negligible. All right, so a downwards input displacement x, where is x? Okay, downwards, okay. X, move the control valve. Here is the control valve. This move x. There is a valve. Okay, pressure go in. You may go to the pistons and so on, right? Returns and so on. Okay, so the downwards input variables move the control valve. Thus, the fluid pass from the upper part of the cylinder, and the pistons is forced to go downward. Okay, so we will go and push, right, when this move down. Okay, so this valve move down, so we will go in and push the piston to go downwards. Okay, a small low power displacement of xt cause a larger higher power displacement of yt. Okay, so when we just move this xt, small xt, then we will get a higher power of yt, right? So that is what it means. Okay, so it's related to the volumetric flow rates q. Okay, and we try to relate it to the input displacement xt and the differential pressure across the piston. Here, as described by this, therefore we will write it in this form. Is related to the volumetric is related to the xt and the differential pressure, right? So let's simplify them, and it must be written as kx minus kpp, right? Then we also know that the volumetric flow rate is related to volume, right? So it is related to a constant area, the area of the pistons, okay, and how much it's go up and down, okay, dy over dt. That would be the amount of fluids flowing. So q can be represented by this, okay. So from this diagram also we would use another relationships, okay, to help us. Okay, we will know that the force, okay, the force give, we will say F equals to ma, something like that, right? So this force is acting on this piston, right? So this cylinder itself, okay. Therefore this force can be equals as AP, okay, AP pressure multiplied by the cross-sectional area, and it should be equals to MA, okay. So this is the A, the accelerations of the piston going down, plus the damping part, okay, B dy over dx, okay. There is a maybe damping, okay. So this is a basic relationships, okay, or the dynamic response, okay. So what we need to do next would be we can maybe substitute, okay, further, okay. We can substitute P as such, okay, and later on we also substitute the flow rate given by the area multiplied by the velocity, okay, of these pistons going down at that time. Okay, put this in relationships, okay. So slowly from there we will get these relationships, right? So at here we would want to check what is the input response and the output response, right? So you will see that it would be ys over xs, okay. The y is our output, x would be our input, remember, right? So rearrange in that order, then we will get this this form of transfer functions where they are given, where k and b has been defined as such. Here are 3 tutorial questions that you can try it on your own. Since these questions would help you to refresh or revise what you have learned in the differential equations and how it's now being applied in this course, okay. So you can try these 3 questions on your own, okay. Since tutorial class will be on tomorrow and the time is limited, I will give you 1 week, okay. So we will do the tutorial class on the following Friday, not this Friday, okay, so that you will have 1 week to deal with it, okay. But in between you can always post questions to the Google Classroom to discuss if you face any problem there, right? I hope that would give you a sufficient fundamental to progress in this course in the later stage, right? See you again. Bye.